Let us start our today's lecture on soil dynamics. We are continuing with our module 5, that is machine foundations. A quick recap what we had studied in the previous lecture. We had seen the application of EHS theory for the analysis of design of machine foundation to compute the displacement amplitude at operating frequency for vertical mode and horizontal mode of vibration for block type machine foundation for 3 different types of soil in case of both types of excitations like constant force type and rotating mass type excitation. Also we have seen the examples, we have worked out the example for rocking. Now, let us come to the next mode of vibration, that is yawing or torsional mode of vibration. So, for yawing or torsional mode of vibration, first step again to calculate the equivalent radius. So, R naught. What is the expression for R naught for torsional mode? 4th root of 16 C D C square plus D square by 6 pi. Am I right? That was the expression given earlier also to you. So, 4th root of 16, 75 by 2, 90 by 2, 75 by 2 whole square plus 90 by 2 whole square by 6 pi. So much of centimeter. How much it is coming? 47.08 centimeter. Okay. So, next step is to calculate the expression or value for I theta. I theta is nothing but half m r naught square, because it will behave like a circular disc, isn't it? So, mass moment of inertia for a circular disc about its vertical axis will be nothing but half m r square. So, half pi r naught to the power 4 h rho, and expression for b theta, that is modified mass ratio, is I theta by rho r naught to the power 5. So, if we put this expression of I theta in this expression for b theta, we will get b theta simplified as half pi h by r naught. Here also you can see b theta is just function of h and r naught only. Okay. So, h is given as 15 centimeter and r naught just now we have calculated 47.08. So, b theta we can easily get the value of b theta, which is coming out as half pi into h is 15 and r naught 47.08. So, how much it is coming? If we calculate it, it is coming as 0.5. Okay. And next is the value of damping ratio. Damping ratio eta theta is given by the expression 0.5 by 1 plus 2 b theta. So, 0.5 by 1 plus 2 into 0.5 is the value of b theta. So, 0.25. And I theta is how much? Half pi 47.08 to the power 4 times 15 times rho, which is giving us 1.1576 into 10 to the power 8 rho. So, for 3 cases we will get I theta with g equals to 50 as 1.1576 into 10 to the power 8 into 1.7 into 10 to the power minus 3 by 981. So much of what is the unit? Kg centimeter second square once again. Okay? Kg means kg force here we are considering. So, if we calculate this, how much we will get the value of I theta for g equals to 50 kg per centimeter square? It is calculated as 200.6 kg force centimeter second square. Okay. Similarly, the other two values of I theta for g equals to 100 will be 212.4 kg centimeter second square, and I theta for g equals to 200 will be 236 kg centimeter second square. Now, next is expression for k theta, the stiffness, that is 16 by 3 g r naught cube. So, k theta for g equals to 50 will be 16 by 3 into 50, r naught is 47.08. How much we are getting? 27827750. Okay. What is the unit? Kg force centimeter. Again, this is a torsional spring. So, it should have this unit. Okay. Next, for k theta with g equals to 100, just change will be, this one will become 100. So, linearly proportional double of this. So, we get 55655500 kg force centimeter, and k theta for g equals to 200 double of this. So, 1.11311 into 10 to the power 8 kg force centimeter. So, what is next step? Next step we have to calculate the natural frequency. So, let us calculate natural frequency. Omega n should be root over k theta by I theta. So, omega n for g equals to 50 should be, k theta for 50 is 27827750 by I theta for 50 is 200.6. So, how much is omega n coming? 372.45 cycles per second. Okay? And other two values of omega n, similar way we can calculate omega n for g equals to 100 coming out as 511.89 CPS. Okay? And omega n for g equals to 200 686.8 CPS. Now, given again we have omega value as 157.08 CPS and T theta is 1414.8 kg force centimeter. It is given to us. So, for constant force type, excitation, the expression to calculate A theta will be T theta by K theta by root over 1 minus omega by omega n whole square whole that square plus 2 eta theta omega by omega n whole square. And what should be the unit? It will be radian once again, because it is a torsional displacement. T theta and k theta have same unit, it will give the radian, that is angular displacement. So, A theta what we were calculating for the first type of soil with G equals to 50 kg force per centimeter square is coming out how much? T theta is 1414.8 divided by k theta is 27827750 root over 1 minus 157.08 by 372.45, that is the omega n we had calculated whole square plus 2 into eta theta we had calculated 0.25 times 157.08 by 372.45, that whole square. So, so much of radian. If we calculate this, in this case we are getting 6 into 10 to the minus 5 radian. Okay. Similarly, for A theta with G equals to 100, T theta remains same, this becomes double, this omega remains same, omega n changes, eta theta also remains same, this one changes. So, by calculating how much we are getting? A theta for G equals to 100, 2.77 into 10 to the minus 5 radian. And remember, these rotations are twist actually, angle of twist. So, linear dimension you can accordingly multiply to get the with check with 0.2 mm criteria. So, A theta for G equals to 200 will be, by putting corresponding value, we are getting 1.332 into 10 to the minus 5 radian. Okay. Now, let us see for rotating mass type excitation. So, for rotating mass type, excitation, the values, first let us write the expression for of A theta, then we will calculate the values. M E E Z by I theta times omega by omega n whole square root over 1 minus omega by omega n whole square, that square, plus 2 eta theta omega by omega n whole square. So, A theta for the first case with G equals to 50 should be, this is 75.1, 7.5, 981, 200.6 into 157.08 by 372.45 whole square root over 1 minus 157.08 by 372.45 whole square whole that square plus 2 into 0.25 into 157.08 by 372.45 whole square. If we calculate this, we are getting 6 into 10 to the power minus 5 radian. So, this is a kind of cross check also I can say, that at same operating frequency with same load, both the cases should lead the same result. If it is not, then there is some mistake somewhere in the calculations. So, no need to calculate for the other two cases, other two values also will be same like constant force type, which are 2.77 into 10 to the minus 5 and 1.332 into 10 to the minus 5 radian. So, with this we have come to the end of this problem, that is for rocking and yawing mode of vibration, how to calculate the displacement amplitude at operating frequency using the elastic half space model. We will continue further in the next lecture with the problem of elastic half space model using the proposed design charts of Leismer's analog to calculate the displacement amplitude at resonant frequency and also to compute what is that resonance frequency for the machine foundation. So, this is a kind of half check we have done, that is at operating frequency we have calculated the values. Like you remember, for the previous case of mass spring dashpot model also we have calculated displacement amplitude both at operating frequency as well as at resonance condition. So, here also we need to do that. So, that we will continue. We will now try to solve this problem, which is again a design check problem. What the problem statement says, the same problem we are taking, only difference, instead of displacement amplitude at operating frequency, now we want to compute displacement amplitude at resonance condition and also what is that resonance frequency. These two informations we want to compute using elastic half space theory. Okay. So, the problem statement goes like this: a block type machine foundation is designed in such a way that the weight of foundation block is 0.25 ton and weight of machine is 0.5 ton with foundation block area of 75 centimeter by 90 centimeter and height is 15 centimeter. So, this basic information is same like previous problem. Now, using elastic half space theory, find out the displacement amplitude and resonance frequency at resonance condition. So, this is the new thing which we are going to compute. Earlier we computed for operating frequency condition what are the displacement amplitudes. Now, we are computing it for resonance condition. For which mode of vibration? For vertical mode of vibration we need to compute. Consider amplitude of external dynamic load is this much kg and Poisson's ratio of soil is 0.25. Again 3 types of soil we need to consider with different values of G shear modulus 50 kg per centimeter square, 100 kg per centimeter square and 200 kg per centimeter square. And again for both constant force type and rotating mass type excitations, we are going to compute this displacement amplitude at and resonance frequency at resonance condition. So, let us start with our solution. We are solving for vertical mode of vibration. The equivalent radius of circular foundation R naught we had already computed, which is 46.35 centimeter, already we had computed for previous problems, and also for different G values of soil, 3 different unit weights we had assumed. Now, next step is to calculate the modified mass ratio BZ. So, using Leismer's analog, which is based on basically elastic half space theory. The Bz value we need to compute. The expression for Bz is given like this. Which we can rewrite as mass to weight we are multiplying by g, here also density to unit weight we are multiplying by g. So, for 3 different types of soil we can get 3 different values of Bz. For g equals to 50, what we are getting 1 minus this mu value is given to us 0.25 by 4. What is W? 750 kg force, and how much is our gamma? We have considered for this type of soil 1.7 into 10 to the power minus 3 kg force per centimeter cube times 46.35 cube. So, it will give us obviously non-dimensional value. How much was the value? Earlier also we had calculated this Bz 0.831. Okay. Now, next 2 other types of soil. For Bz with g equals to 100, we need to change which value? This will become 1.8, all other values remain same. So, if we calculate, it is coming 0.785, and Bz with g equals to 200. For that, in this expression this value will change to 2, hence the value is coming 0.706. Now, how to get the displacement amplitude at resonance condition? For this, remember we had shown the design charts given by Leismer at resonance condition, how to compute the displacement amplitude. It is given by Richard. So, this chart we have to look into. Let me place the chart here. Can you see this chart? I had shown earlier. Bz, consider the vertical mode of vibration. Now, this Bz value we have computed for 3 different types of soil, from which we can compute magnification factor mm or mrm, whether we are considering constant force type or rotating mass type excitation. And this is the equation we need to use to get the value of displacement amplitude. So, this dotted line is for constant force type excitation and the solid line is for rotating mass type excitation. And look here, it is mentioned in this design chart that the limit of Leismer's analog is the value of Bz 0.36. If Bz is below 0.36, then we have it is constant at 1. Otherwise, above 0.36, for mrm it remains 1 up to a certain value, then increases. However, for constant force type it increases from there itself. Okay? Read the design chart carefully, which I had already shown earlier also. So, now looking at this design chart, what we get? We get the values of mm for g equals to 50, which I am reading for Bz value of 0.831. So, corresponding to 0.831, if we look here carefully, for 0.831 somewhere here, we bring it to this curve and drop it down, and also for mrm. So, by doing so, I am able to read the value of mm as about 1.25, and For rotating mass type excitation MRM, that also I am reading about 1.25 from the design chart. For G equals to 100 is 0.785. So, by using the design chart I am able to read it is 1.18, whereas for MRM at G equals to 100 I am reading the value as 1 itself, because you can see it is about 1 MRM for this value. Similarly, for G equals to 200, I am reading the value from the design chart as 1.15, and MRM for G equals to 200, this also remains 1. Okay. It will be better always if the available design chart you can blow or magnify and then read using scale properly. Then it is better way to read the correct values. Now, let us use the available equations with us to compute the displacement amplitude. For constant force type excitation, the expression is AZM is given as 1 minus mu q naught by 4 g r naught times This is given here. If you look back here, AZM is this expression, it is given in the design chart also. So, now the values of q naught given to us 188.64 kg force, and mu is also given to us 0.25. G will change for 3 different types of soil, and R naught also we have computed as 46.35 centimeter. Therefore, the value of AZM with G equals to 50, how much we are getting? 1 minus 0.25, 188.64 by 4 into 50 into 46.35 into How much we read from the design chart? It is 1.25. So, 1.25. What is the unit we should have from here? It will be in centimeter unit. Am I right? Because G is given in kg force per centimeter square, R naught is in centimeter. So, centimeter goes up. So, calculate this, how much we are getting the displacement. It is coming 0.01908 so much of centimeter, which is 0.1908 millimeter. Am I right? Which is less than 0.2 millimeters, hence okay. Again a cross check with our permissible displacement. And as we know, though this is not the case going to occur, because it is not at operating frequency, but to be always on the safer side, we can cross check this also. Similarly, for other 2 types of soil, AZM with G equals to 100 should be, what are the changes? Let us see in the equation. This remains same, this remains same, 4 into 100, this will become 100, this remains same, and this value also changes, whatever we read from the design chart, that is for 1.18 for G equals to 100. If we put the values and calculate, how much we are getting? 0.09 millimeter. And AZM for G equals to 200. What are the changes in values? Let us see again. This will become 200 and this value we have read from the design chart as 1.15. So, put it there. After calculating, we are getting it as 0.044 millimeter. Now, for rotating mass type excitation, what is the expression to find out AZRM? The expression is MEE by M times MRM. Now, how much is this MEE by M? This remains same for all types of soil. 75 into 0.1 by 750. We can take it as eccentric weight and total weight. So, 0.01 so much of centimeter. Fine. This expression is already given in our design chart also. What we have seen for rotating mass type excitation, this is the equation to compute the displacement amplitude. So, with this, how much AZRM we are getting for G equals to 50, 0.01 times MRM. MRM, how much we read from the design chart for G equals to 50, 1.25. So, let us multiply this with 1.25 so much of centimeter. So, which will give us 0.125 millimeter. Similarly, for other two types of soil, MZRM with G equals to 100, 0.01 into the factor MRM we read for this as 1. So, it is 0.1 millimeter, and also it remains same for G equals to 200 also, because this factor remains same. So, 0.1 millimeter. So, these are the displacement amplitude at resonance condition. What about now resonance frequency? That also we need to compute, right. So, for computing resonant frequency, what we should do? Resonance frequency, again we have to use the design chart. So, for BZ values, different BZ values with G equals to 50, 0.831, BZ with G equals to 100, which is 0.785, and BZ value for G equals to 200, which is 0.706. What we are getting? The values of A naught M. Now, we should look into this design chart, which was again I had shown earlier in my previous lecture, that corresponding to BZ value, we have for constant force type excitation and for rotating mass type excitation different curves, dotted and solid, from which we can get this A naught M. So, let us read these values A naught M. So, A naught M for this G equals to 50, let us first consider only for constant force type excitation. So, for constant force type excitation, that means in the design chart we should look into the dotted line, right. How much we are reading? For the first one I rate the value as 0.78. For the second one, A naught m with g equals to 100, I rate the value as 0.75, and A naught m with g equals to 200, I rate the value as 0.74. Now, these are the values of A naught m, from which we are supposed to calculate the frequency in RPM unit. So, what are the resonant frequency now we can calculate? Now, this A naught m is written like this: 2 pi f m r naught root over rho by g. This A naught m now already we know from this design chart, r naught known, rho we have assumed, actually gamma we have assumed. So, take care of the unit properly, g also known for 3 different types of soil. So, f m for g equals to 50, how much we are getting? Please put the values. A naught m was 0.78. So, how much we are getting? After calculating this, I got 863 RPM. Is this okay? Initially, FM you will get in hertz, that you need to convert to RPM, because check about the units. Is it okay? So, now for other 2 types of soil, FM with g equals to 100, if I calculate, I get this value, and for FM with g equals to 200, if I calculate, I am getting 1510 as RPM. So, remember, when the same foundation we are planning to operate at operating frequency of 1500 RPM, for this third type of soil, usage of it is ruled out, because the operating frequency then will be very close to the resonant frequency, which should be avoided as per the design criteria. Whereas, for this type of soil it is allowed, but this type of soil also it is somewhat permissible. So, remember how much factor of safety we are planning to provide. Depending on that, you can decide and give your judgment. So, here your judgment will come into picture, because when you are commenting on the design aspect, looking at this resonant frequency, you have to give comments on where to keep your operating frequency, in which range, and so on. So, that is why this computation of resonant frequencies also plays an important role here. Fine. Now, for rotating mass type excitation, let us see how much we are getting. So, for rotating mass type excitation, we have BZ 50 as 0.831 from the design chart. A naught m for this g equals to 50. Let me show the design chart again. Now, we are going to read this solid line. From this solid line, BZ corresponding to 0.831, we will bring it here and drop it and read the value. I am reading it about 1.4. So, how much is the value of Fm with g equals to 50? Fm will be A naught m 1.4 divided by 2 pi, r naught is 46.35, root over g is 50. I have to multiply it with 981, that is acceleration due to gravity, to take care of the unit weight here. gamma instead of rho. Okay. So much of CPS, cycles per second, which we need to convert it to RPM. So, 1549 RPM. Now, calculations are clear. Next, for Bz corresponding to G equals to 100, we have the value as 0.785, which from the design chart will give us A naught m. I am reading it as 1.5, which means f m for G equals to 100 after putting this value in this same expression. The changes will be, this is 1.5, this is 100, this is 1.8. Okay. I am getting as 2281 RPM, and for Bz with G equals to 200, the third type of soil, we got the value already 0.706. Now, using the design chart again, the value of A naught m is calculated or read from the design chart as the same 1.5, there is no change, which gives us f m with G equals to 200. In this same expression, the values are changing, like this is 1.5, this is 200, this is 2. So, it is coming about 3061 RPM. What does it mean? Looking at the three values, we can conclude that as a designer, what we can comment, that the for first type of soil, if we plan to run or operate the machine at 1500 RPM, it may lead to close to resonant condition, which can be avoided. However, for the other two types of soil, it is pretty okay, because resonant frequency is far from the operating frequency. So, these are the conclusions or design guidelines what we can propose from these calculations. Now, let us come to the next problem. Next problem, the same problem we are considering, only we are taking care of now another mode of vibration, torsional mode of vibration. And in case of torsional mode of vibration, as we know, the amplitude of external dynamic load should be torque. So, that applied external amplitude of dynamic torque is 1414.8 kg centimeter, kg force centimeter. Okay. Again, for three different types of soil, we have to find out the displacement amplitude and resonance frequency at resonance condition using this elastic half space theory. So, the same problem now let us start solving for torsional mode, torsional or yawing mode. Torsional mode of vibration, R naught already we had computed earlier for torsional mode. Using the known relation to convert the rectangular dimensions to equivalent circular radius. This already earlier we had computed for the similar problem, and the expression for k theta, that also we had used this one, and expression for b theta, that is modified mass ratio, we had used I theta, which is mass moment of inertia, rho r naught to the power 5, which we had computed as 0.5. Refer to our previous problem, you will get these values. So, I am not calculating it, I am not repeating it. Now, for this b theta equals to 0.5, let us look at the design chart, which was again given to us earlier. Let us refer to the design chart of Richard's book for torsional mode of vibration. So, which design chart now we should follow? This one. For torsional oscillation, B theta is we have computed just now, m theta Rm for dotted line, that is rotating mass type, and m theta m is for constant force type, the solid line. And the expression to compute a theta m and a theta Rm are given here. So, let us use those for B theta equals to 0.5. From this design chart we get m theta Rm for rotating mass type is for R and constant force type is without R, is 1, and m theta m is about 2, that I am reading for B theta equals to 0.5 from that design chart. Okay. Now, what is the expression for a theta m? A theta m is nothing but T theta by k theta into m theta m. Do you agree with me? For constant force type excitation, this is for constant force type excitation. Look at the design chart, it is also given in the design chart. A theta m is 3 by 16 T theta by g r naught cube m theta m. So, g r naught cube 16 by 3 is nothing but k theta, is not it? So, T theta by k theta m theta m. So, k theta different values already we have computed for our previous problem, the same value we can use. Let me quote those values once again. K theta for g equals to 50 we had computed as 27827750. So much of what? What was the unit we had calculated earlier? What was the unit for this? Kg force centimeter, right? K theta for g equals to 100, double of this. So, 5565500 kg force centimeter, and k theta with g equals to 200 we had already computed, double of this, 1.11311 into 10 to the power 8 kg force centimeter. So, with these known values, T theta is also given to us, which is 1414.8 kg force centimeter. We will get A theta m for first type of soil will be 1414.8 by 27827750 into m theta m, how much we read? 2. So much of radian. Am I right? Units are consistent. So, it is giving us 1.017 into 10 to the power minus 4 radian. As I said again, this angular or torsional displacement we can compute it in terms of linear dimension also by multiplying corresponding length. And A theta m with g equals to 100, corresponding g value has to be placed. M theta m we did same for all the cases. So, it will be 5.084 into 10 to the power minus 5 radian, and A theta m with g equals to 200 comes out to be 2.542 into 10 to the power minus 5, so much of radian. Now, for rotating mass type, excitation. What is the formula? We should use A theta Rm is MEEZ by I theta times m theta. So, for rotating mass type excitation, A theta Rm is expressed as MEEZ I theta by I theta times m theta Rm. If you look at the design chart, you can also see A theta, this should be Rm, okay, in the design chart for rotating mass type, m theta E times x, that is the lever arm, and by I theta m theta Rm. So, A theta Rm for first type of soil G equals to 50, how much we are getting? 75 into 0.1 into 7.5. I theta we had calculated earlier. If you refer to our previous calculation, I will remind you, I theta we had calculated as I theta for G equals to 50 was how much? 200.6 kg force centimeter second square. So, that we have to use, and m e is mass. So, 75 by 981 into 200.6 times m theta Rm is 1, we have read from the design chart. So, it is coming as so much of radian. If we calculate 2.86 into 10 to the power minus 4 radian. Okay. A theta Rm for other two types of soil with G equals to 100, by putting the values of corresponding things, all this remain same, only change will be in I theta. I theta for G equals to 100 we had calculated earlier 212.4. So, I theta for G equals to 100 was 212.4 kg centimeter second square, and we had calculated I theta for G equals to 200 as 236 kg force centimeter second square. This already we had calculated in the previous lecture. So, this will give us 2.7 into 10 to the power minus 4 radian as the torsional displacement, and A theta Rm with G equals to 200 is computed as 2.43 into 10 to the power minus 4 radian. So, these are the displacement amplitudes at resonant condition. Now, what is that resonant frequency we need to compute? So, resonance frequency for the value of B theta we had calculated as 0.5, A naught m we need to calculate for this B theta equals to 0.5 from this design chart. This is the design chart earlier I had shown, and I had also mentioned that in this case torsional mode of vibration, both rotating mass type and constant force type, they are giving almost the same values. They are changing marginally at the very high value of A naught m or very low value of B theta, in other words. This dotted line is for rotating mass type excitation and the solid line is for constant force type excitation. And expression for A naught m is also given here. So, if we read carefully, I am reading the value of A naught m as 2.1. Now, A naught m is 2 pi f m r naught root over rho by g, that is the expression. So, f m will be A naught m by 2 pi r naught root over g by gamma. So, f m for g equals to 50 for constant force type excitation. This is for, let me mention, it is for constant force type excitation. So, this comes out to be 2.1 by 2 pi r naught we had calculated as 47.08 root over 50 into 981 divided by 1.7 into 10 to the power minus 3, so much cycles per second, which we can convert it to RPM, 2288 RPM. Am I right? Similarly, for next type of soil, F m with g equals to 100. What are the changes? Let us look at this expression. A naught m remains same 2.1, 2 pi, this also remains same. Here it changed to 100, this remains same, it becomes 1.8 gamma. So, the corresponding value of F m comes out to be 3144.5 RPM, and F m with g equals to 200, the value can be calculated as this all remains same, here it becomes 200, here it becomes 2. So, the value is calculated as 4219 RPM. So, what is the comment we can provide here as a designer? That resonant frequency for all the 3 different types of soil are far away from the operating frequency, proposed operating frequency or given operating frequency by the manufacturer of the machine, that 1500 RPM. So, in torsional mode, the design for all 3 types of soil are pretty safe, whatever the size of the foundation, everything was provided, they are very safe, because both the displacement as well as the no resonance criteria are satisfied. We will stop our lecture today here. We will continue further with our lecture in the next class.